Okay, welcome everybody in this world of home office. And let's start. My name is Nicolai Josuttis, and I want to talk about C++20. I have a couple of things to tell, things I learned. I don't know everything about C++20 yet, but I'm writing a book, and so I learn a lot. I even try out details. And the reason for this talk is I want to come up with the most important and nicest examples I found so far. So let's go. Let's first look at concepts and requirements. The first thing I want to show you is this, just this. What is this? This is a function, an ordinary function, not a lambda, taking generic parameters. But we don't do that the usual way, that we declare a template and introduce template parameters. We just declare the parameters to be auto. So that's the first feature we have. And by the way, this is not a lambda, what you see on the left. It is a function template. So it's really equivalent to the things on the right, except that we don't have a specific name for the types T1 and T2. So let's use it. This is a function that can insert a value into a collection. So let's create a vector and let's call it, and it internally uses pushback. So that works fine. However, if you try to call this for an unordered set, it will not work because we have no pushback for unordered sets. So what can we do here? We have here an ambiguous situation. Remember that the compiler in overload resolution to call a function only looks at the signature, at the declaration of the function. Both look the same. There's nothing to prefer. So how can we solve this problem? Well, the new way to solve this problem, especially if you have an auto parameter, is you qualify it. You put a requirement, well, we call this a type constraint in front of auto. And you see it here. The type constraint is hash has pushback. And this, by the way, is equivalent to the following, which you can also do now. If you want to, instead of writing this as a function taking auto parameters, you can still declare the template parameters explicitly and qualify them instead of using type name, using hash pushback. Okay, so where does this hash pushback come from? Well, it's a concept. It's one of the key features we now introduce in C++20, but it's not only about concepts. You not always need for everything a concept for a type requirement. But if you want to qualify a specific type, if you want to have a type constraint, as you see here, then you need a concept. And the concept is declared here or introduced here, defined here. It is defined as a requires expression. The requires expression says, so if I assume for the collection I'm checking this for, it is a collection and I have a value type of this collection, can I call pushback? So what we check here is this a valid call? And if this is a valid call, this concept is true, is satisfied. Well, at the end, a concept is a Boolean compile time expression. So at the end, we check, is this true or not? And if we use that as a type constraint, we check about the type here, whether it fulfills this requirement. Is this true or not? Which is the case if we pass a vector, which is not the case if we pass an unordered set. So you might think about, wait a minute, it's clear that if I have this type constraint that and it isn't fulfilled, that the second declaration is only used. But if you call this for the first in the first case, so passing a vector, both adds are valid because we have an add here that has a type constraint, and we have here an unconstrained auto parameter. So it works because in overload resolution, we prefer more specialized type constraints. In general, we prefer more specialized concepts. We have a feature that is called concept subsumption. You can even create a hierarchy between concepts and say this concept implies the other one. So in that case, it's a stronger requirement if I use it somewhere. Good. So far so good. The only interesting thing with this example, don't do that. And the reason is, if we would introduce a concept for each and every member function, just check, is this member function available? We would introduce a lot of concepts. Please note that this is not generating code. That's, by the way, the reason we don't pass the collection here as a const reference or by reference. It is just to check whether this generic code is available for this type or not. If the compiler has to check this, and if we would introduce thousands of concepts, compile time goes down. So especially as I just told you, concepts can subsume each other. So the compiler even checks whether indirectly concepts have requirements that are a subset of another concept having requirements. And so what can we do instead? If I say, no, don't do that. Just introduce concepts for the broad things, for saying this is an input iterator, or this is a pointer I want to read from, or this is an object I can call, something like that. We introduce standard concepts for that in C++20. So here's another way to use a requirement, not using a concept. We are just using what you see here on the right, more or less. And look at this. This is what you can do now. Because we use the same signature, the only difference is in the implementation of the function. And since C++17, we have compile time if. And compile time if works very nicely with requirements. And so you can just say, if at compile time we know that the requirement that for this object, I can call pushback passing this as a parameter. If that is true, that requirement is satisfied, then we call pushback, otherwise we call insert. And I'm pretty sure we will see that in a lot of places in the near future in C++. So that's my first favorite code example. Let's go to the next one. Let's talk about ranges and views. So what is a range? A range is something a lot of people are waiting for years now, for centuries maybe even, because they were always complaining, why the hell do I have to pass two arguments to sort if I want to sort thus all elements of a collection? Why can't I just say sort the collection? And yep, here's the answer, because we have introduced something, and that's ranges. These are objects, and that ranges, and these objects take ranges. Well, a range is more flexible than you think at first. So we will see that in a moment. But let's start with a simple case. So the simple case is like here, that we, for example, pass a collection that has a begin and end API. However, please note that this sort is not in the normal namespace std. It's part of the sub namespace std ranges. The whole ranges library, including a couple of utilities, comes in the sub namespace because we had some problems with symbol conflicts and overload resolution in certain scenarios. So let's use such a range like collection or others somewhere else. So let's, for example, call a function print, pass a range, and for this range, call for each, which is another rangified standard algorithm like SORP. So you see again, this for each in a namespace ranges takes a range as a whole, not begin and end. And we pass this. And here you see, by the way, of course, an application of concepts. That's one of the standard concepts we have introduced. So as a requirement, as something that is checked, as something that is documented, we have a concept here that qualifies this argument that it has to fulfill the requirements of input ranges, which guarantee that you can read from this range the values. So can we call it? Yeah, you simply pass the container to this print. And this print tags the range, the whole collection. We call for each for it, printing out all the values and putting a new line at the end. So think a little bit about what's happening inside in this ranges for each code. So in this ranges for each code, we don't use range.begin and .end, which would work perfectly fine for this collection. So for a collection, we can call begin and end, and you would assume this ranges for each calls internally begin and end. But we call something different. We call std ranges dot colon begin and std ranges colon end. Why that? Because this is a helper utility of this ranges library, and it makes the code even more generic. You might have seen already in C++ std begin and std end and the freestanding name as a freestanding function to support arrays. And here it's the same, although that in the ranges namespace, we have even more flexibility, as you will see in a moment. So some of these general helper utilities we already had for ranges, we now have again in the ranges sub-namespace, and please use them for this concept. So here's one thing you can do. You can say, okay, let's take an array, a raw array, here a raw array of strings. Yes, we can sort it, of course, and we can print it, sort and print both, use these helper functions and to get the begin and the end of the raw array, which are the raw pointers to the first element and the position behind the last element. But this is not all. I mean, we had that for std begin and std end. So we have more. Well, those who invented this concept, this feature, have introduced more. And one interesting thing they introduced was sentinels. So far, if you look at this code, there is something in common with the begin and the end of a collection, or with the begin and the end of an array. They have the same type. But that's no longer required. You can say, okay, the end iterator, so the thing that marks the end of a range does no longer have to be the same type. And here's a pretty simple example for that. That is a very generic data structure that defines an end iterator, a generic end iterator, which just defines the past value, the value you pass to the template, defines the end of a range. So how do we implement, how could we use it? So we want to use it like something like this, but this will not compile, you will see it in a moment, but that's the idea. The rough idea is to say, let's start from the begin, iterate over all the elements, and we have to sort all the elements until the last element of the range we want to sort, and that should be the element with the value -1. So we would only sort these 5 elements. So we create an object of this type. Now remember that we internally compare again and again iterators with this. So we need an equality comparison for this helper end iterator, this helper type. Please note, although the algorithms check for not equals, and the order might not fit, so that the first operand is the end value and another argument, another operand is passed as second. This is enough because we have in C++20 special features introduced for comparisons. And the first things we introduced were, if you declare define equality, you have defined not equality, or that something is not equal. And even more, the compiler, if it cannot compile equality checks in the order you have, the compiler will rewrite your call statements to try the opposite order. So by having just this equality check, we have introduced all these different checks. And if you have something like this, this might be is rewritten to this. So still, if you have a not equals operator, that would have higher priority, but this is enough. So we have introduced here everything we need to check for equality between an end value and something we pass. And this something we pass is an iterator. And so for any iterator of any type, we look at the value and see whether the value fits this. And then it's true. So the end iterator, or a comparison with this value, is true if the current iterator points to this value, which is exactly what we want to have. We want to check whether when we go to and want to sort all these elements, let's sort them from begin, and this defines the end. If we compare with this, that's the end. So unfortunately, that doesn't work. I told you, yeah, we have some functions already in std functions in the std namespace, and also helper functions may be used, but maybe not. So they are still the same. They are not modified. And they require that begin and end have the same type. But the sort and range list does not. So the sort and range list now takes the begin and this end, and it works fine. Let's sort all the elements from here, from the begin of this collection up to the value -1, which is the end of this of the end iterator, defining the end of this collection. Now, can we also use our print function, our print helper function for that? Well, yes, you have to define a range. So how do you combine these two things into a range? That's simple. There's a type called subrange. Unfortunately, it's called subrange, not range, but you create a range, which might be a subset of an existing range. And that is all you do. You initialize a range. Please note that this range is a view. It refers to the collection. You don't create a new copy of all the elements in call. You just create something that is all the elements, or represents all the elements from begin to this end value. And then you can call range, can call sort for this range, or yes, you can call print for this. And that works fine. It's an input range we can read from, so the requirements fits, and we can pass it to the for each algorithm, which takes such a range, so a range where the begin and end types differs. So please note that at the end, what the for each now does, it will iterate over all the elements from begin to end to find the end, and at the end, it will compare the current position with the end value. And the end value here is defined by this. And as you see here, we use a not equals operator which is defined indirectly by the equals operator, and with the end value a second operand. So according to rewriting, what is really called is having the operands in a different order with a not in front. Are we done with this example? No, there's more. Well, first of all, please double check that if we have created a range, it's just a view into the existing range. So we have modified the original collection. We have not modified a new range. So this is a cheap operation to create such a range. And here is one more example. So let's assume what we want to compare is elements in a container, and the elements are data structures like 3 doubles, just coordinates, X, Y, and Z coordinates we have here. Just it could be an aggregate even, like here. And we have an STD array of a couple of coordinates, some points, 3-dimensional points. So let's use them. Can we call sort? Yes. No, we can't, because less than is missing. Sort needs less than. So do we have to introduce less than here and then all the other different comparison operators? No, because like this is enough to introduce equality checks, including using operator not equals. We have even a more shortcut scenario, or a different shortcutting scenario, which is this. Let's use the new spaceship operator. And if you have a defaulted spaceship operator, that's a very special rule, then you have introduced all 6 comparison operators, provided all your members are public. So in this case, we have introduced all 6 of them. You can also implement it and to define comparisons. And again, 1 operator would be enough for the relational operator. Then this would be for the equality checks. And so 2 for 6, including that automatically things like cons X with no except and type conversions for the first operand are possible by rewriting or changing the order of the operands. So that works. We can sort. Okay. Can we also call print for that? Yes. Well, let's look at this. Let's print all the elements from the beginning of this array. So from the first coordinate after it was sorted, the whole array, to this element. So the end, as an end, we use this end sentinel, this end iterator having a different type. And the end we define by passing, the end should be the coordinate 4, 5, 6. So is that possible? Yes, since C++20, it is possible. That was not possible before, because since C++20, non-type template parameters, so values of a class, of a data structure, can be template parameters as long as these are literal types with just public members, which is the case here. So this works. Yes, it works. Well, no, doesn't work yet. Yes, we can pass this, so we can create an end value. We can pass its range to print, but of course, print internally wants to print out the elements. What else can we do for that? Well, we need an output operator. I hate it. When I write an output operator for this, I have to write to stream shift of the output operator, then c.x, then I write out the slash, then c.y, then I write out the slash. I have a couple of times using this operator. Is there something new we can use? Of course, you know how this talk is running. We have a new feature that's for formatted output, finally. So all you have to say is, let's create a string we print out. And in the string, we have placeholders for the following 3 arguments. Take the X, the first argument, the second argument, and the third argument, which are the X, Y, and Z coordinates, and put on slashes in between. Yeah, that's it. That's my second example. Well, but there's a bonus track to this example. And the bonus track is, as you have seen, a sub-range creating a view referring to the original elements in this array from the first element until this element excluded. We have other, what we call views. And views are lightweight, well, views into containers, into ranges, to make it more general. Like a string view, which we introduced in C++17, is a view into the characters of the string. We can now have views on both readable and writable, referring to some container, and they can do some more interesting things. So let's take this, for example. Let's create a view that says, oh, let's take the first four elements of this, and let's call sort. This creates a view for the first four elements, so this, and that is what is sorted then. If we print out call, we will get this output. By the way, this view is smart. This view creates a very special type we introduced, which is called a span. If the underlying collection is a raw array or a vector, well, if the elements are in continuous memory, because then by using type erasure, we can really create a very performing code, eliminate more or less everything from this view. And but we check that, and counted is checking that for us. If the underlying range has continuous memory, all the elements in continuous memory, we use span. Otherwise, we use here another view, which is called a ref view, as far as I remember. So, but that's nothing you have to think about. It's done automatically for you. Can we have other views? Yes, views have a nice way to combine them. So you can, instead of saying, I pass some collection and some parameters, you can say, let's pipe all the elements from this range of view to this, and let's pipe that to here. So let's take the collection, filter out all the elements greater than 0, transform them by computing the square, and let's print that. Yeah. Oh, you can call print now, our print algorithm. Well, unfortunately, that does not work because we have here created something that iterates over the elements of this collection and modifies some things. And to iterate over that, some of these views have a state. And we change the state while we are iterating over the elements. So we need support for mutable views. That's why you can't pass this as a const L value reference. You have to use an R value reference, which with auto in front is a universal reference, or as we in the standard say, a forwarding reference, but the name is really bad. We should still name it as a universal reference, because it universally can refer to objects that are const and not const. You can even pass PR values, so temporary values, but there's nothing with forwarding here involved. So this is just a universal, or if you like, a forwarding reference. Unfortunately, we have both terms now because the C++ standard committee didn't like the term we had established in the community. Whatever it is, but you have to use it now, because if you make it const, this print will not work, because we mutate the state of the elements we are iterating over. And again, this has reference semantics. Again, this is not creating, the view is not creating a subset of the collection at the time when we define it. It's a way that we say, okay, let's define a way when we iterate that we take all this into account to deal with the elements of this collection. So if we print it out now, if print and for each calls begin goes to transform, says I want to have the first element, calls begin here for the filter, begin goes to the collection and says I want to have the first element 42. Is it for if it's passed by the filter, then we have the transformation, and then the first element comes. With plus plus, we get the next element. If the filter does not accept an element, we will not pass it to transform. So if we ask for the next element, filter will go here, find 0. We pass it to the filter say, no, that's not greater than 0. So we come back to the collection and ask for the next element, calling plus plus. So we have a way to, on request, while we are iterating with print or with for each inside, to request the next value, which is then processed by these different views. And that means essentially we have lazy evaluation. So if you add a new value in this collection and then you call print again, you will find the square of this element if it goes through this filter. Yes. So you will have that. So there was one question in the chat, -1. What happens if we don't find this end value somewhere in this? Actually, I don't know. We will never find an end. So we have probably undefined behavior. So don't do that if you are not sure that you have this value at the end. One example where this makes sense would be also, for example, you iterate over the elements of a string and you say the \0, so the null terminator is in that string. Unbalanced parentheses break my brain. I'm not sure where this is the case here, but I might have made something wrong. Yeah. So I read it in the chat as a comment. So we have a couple of standard views. Here's another example, a short example. Assume we have a map where we have composers inside. Some composers string maps to int. That's the name of the composer and it's a year of birth. This is also a sequence of views. So let's take this composer, filter out the composers that were born after or since C700. Then take only the first 3 of them, and they are key value pairs. Take only the keys. These are all predefined filters and views in the C++ standard. And let's iterate over them. The range-based for loop also allows to have ranges now where the end type and the begin differ. We have introduced that, by the way, in C++ 17 already. So if we print them out, we get here Beethoven, Chopin, and Mozart, because they are sorted inside. Yeah, that was the second example. Let's talk about threads. In threads, we have finally now in C++ 20 added a few interesting features. So the first one I want to show you is a barrier. A barrier is one way to say to synchronize multiple threads or multiple areas of asynchronous processing. And so, for example, here we say we have an array of floating point values. Let's use multiple threads to deal with the values. So each thread takes one of them. And whenever the threads are ready, they have done their processing with each element. When they are ready, let's print the current array. So how do we program that? We say this is a barrier taking the number of elements here. As so to say, for each element, we need the OK. And then this will be called as a callback. So this is a thread. This is a vector of threads we create. So let's create all the threads. By the way, it could also be a thread pool, and the pool takes always the next elements until we really all the threads have enough threads have to say yes, we are done. So here, for example, we compute the square root. Each thread computes a square root of one index, which it takes. And here's a call, the important call. So I am done so far. Let's wait until I want to continue. So this time we block. So this would not work with the thread pool because each thread takes care for its own index. So when we are here, we wait for all the other threads to be done. And then if all the threads are done with their values, this callback is called, and then this wait ends. So we continue with this loop and compute the square roots again. And when all the threads are done, we print them out again. So that's something you can do with this. Please know that we can improve this. First of all, what happens if we come to the end of this compute function? Well, there's a really bad design we had in C++, since C++ 11, that threads are not RAII types. So we have fixed that finally, put a J in front, and this J makes sure that if you come to a destructor, you wait for the end of the thread, so you don't have to call join manually at the end of your scope, and even in an exception handler, if in the middle of your function, you leave your scope. So, but there's more. There's a stop token now, and the stop token can be passed from outside. So if we come here after some time, that's something we have to decide. If we come here to the end, the destructor will signal to all the threads in the vector, because the destructors are called, will signal to all of them, please stop. That's a thing you have to check now. Was there a stop requested? And as long as no stop was requested, we process it. But we might have a deadlock, because think about, you have all these 6 threads running, and some of them have stopped running, while the others still wait for all 6 to end until they check again this while loop. So for that, it's important that if you leave this, you say, I'm no longer part of this barrier. I'm no longer part of this game. So you arrive here and say, well, yeah, I'm done. So the counter of the barrier goes down, but please drop me out. So next time, when the other threads are still running, please don't re-initialize the barrier with the full number of threads, 6, but with 1 less for each drop we have. So that way, we don't have a deadlock if something happens. So what else do we have? You can also have binary semaphores now, which can be used, and that's interesting, as a simple signaling or notification mechanism. So look at this here. We have one thread and another thread. You want to signal, I have here something for you to process. So that's a binary semaphore, says, please release. So that another process who can wait, who can try to acquire a resource, so try to acquire access to the in data, waits for this release. So to some extent, a release only adds the counter, and this is counting down. But waiting that way, we have a signaling mechanism, because these are like mutexes where lock and unlock can be in different threads. And that can be used for a signaling and notification mechanism, as you see here. So what else have we have there? There's also one thing I want to show you about atomics. We have now, for atomics, the option that you can have them partially atomic only. It's called an atomic ref. So think about, you have an array of 1,000 elements. Let's initialize them by just one thread. You don't need atomic access for that. But later on, multiple threads deal with the values in this array. So you now create an atomic reference referring to the values in this array. And there, when you then use your atomic operations, you have atomic access, of course, this should not be done while this in the front is happening. So after this initialization, we have full support for atomics, but not the whole lifetime. And finally, note that all the atomic types now have a wait and notification mechanism. Also, we have a lot of wait and notification mechanisms now, so it will be an interesting question when to use which. So that can be used for a fast scheduling system. So think about, you have here a main thread, and you want to have something like threads want to be processed. But in the order of they asked for getting access to some resources. So we enable a ticketing system. So here we say that's my max ticket, and now an actual ticket is 0. And whenever you are in your thread, you want to have access to some resource, load the actual ticket. If it's not yet your ticket, wait and reload again. So in a loop, we wait, but this is no active waiting, no polling, because we have a wait call for the atomic. And here in the main thread, we can say, okay, now let's enable 5 tickets to be run at the same time and notify all of those who wait, and they can check if they are enabled now. And after they are done, they can say, oh, now the next ticket can be processed. And please notify all of them who are waiting so that they double check whether it's their turn now to continue. Okay, that's about concurrency. Finally, a cool new thing is the library for calendars and time zones. That's an extension to Chrono, sometimes called Chrono 2.0. Just some examples as usual. Let's initialize an object with the 1st of January of 2021. There are various ways to write that. This is a full type system that's a type for a year, and combined with this operator and integral value, this is a type year month. And combined with this operator and its integral value, this is a year, month, day. But you could also create it in other ways, like here. And you also have here a year, month, last. So this represents the last day of your month. The difference would be if you here add 1 month, you are still at the 1st. If you start with January 31st and you add 1 month, in February, you would have this invalid date, this ill date, February 31st. But if you increment an object that has the day last to the next month, you get a different day then. So you can use that, iterate from this to this over all the months, print them out. Direct output is now supported for all different chronotypes, even those who existed already. So here we print out the day in some standard format you can influence with ST format, of course. And you want to check, do something special for a special weekday. Okay, if the weekday is a Monday, do something else. Now this looks easy to use, but there are traps. And the traps are, in this case, especially because of performance issues. So we iterate here over all the months of a year. So we have the types year, month, day, and we can easily add the next month. However, if you try to add the next day, 1 day to the date, so let's iterate over all days of a year, this will not compile. Why that? Because in this library, the library is designed for very, very well performance, and computing the next day after might become pretty complicated. So if it's February 28, is it the last day or not? That depends on the year. So we have to double check whether the year is a year with leap days or not. And therefore, the designer of this library Howard Hinnan said, no, I don't want you to that this compiles, because you should be forced to do something more effective. So what he introduced is also another way to represent days. So we have different calendars introduced, and this other day, the other calendar is counting system days from Unix birth. And this is a calendar. There you can add one day, and this all works fine. Here in this case, when we print out the day, then these days are converted into something readable, which because I/O is anyway often pretty expensive, that it's not that bad at that situation. Good. We also have support for time zones. So let's go to the current time zone and take the system clock now. So let's find out what is now in the current time zone. And here we round it to a year, month, day type again. You have seen that before. It's just a day of the month of the year. And now let's create a new day, which is today. That's today here. That's a way to compute today, where it's no simple today can depend on the local current zone, or there are also ways to say, let's use UTC. UTC day might not be the same as a local day because we might have crossed midnight already in our time zone. So things like that matter, and therefore we have this complexity. But here we say, okay, let's take the current zone, compute what is today, take the year and the month, well, next month, plus, and take the last Friday of that month. Okay, that day is Friday next month of my local day. And now let's schedule two things. Let's schedule 2 time points. Time point of a party, of a local party, and time point of an all hands on for the whole company worldwide meeting. So here we use local seconds, which says this is not bound to a specific time zone yet. While here we take system seconds, and they say, oh, this is bound to UTC. So we take our day 6 hours earlier. So that means a local party at 6 p.m. On the day before. And here plus 17 hours. So we have a company call at this time zone, UTC time zone, 17 o'clock. And now let's compute a couple of output here. And for that, we can we have support now from the IANA time zone database. And for example, these are 2 entries possible there. And we can say, okay, let's print out now, bind these time points to a specific zone like Europe, Berlin, or America, LA. And then let's print it out. And yeah, we have support for the format library again. So we can have our format. Remember, in format here now we have curly braces for the first parameter, curly braces for the second parameter. In this case, we print just the time zone with a width of 20 characters, and here an empty string with 20 characters. And then here we have some placeholders for this local a representation, like in a string f time, strf time. So like here %d or %r, and we got this output. And yeah, of course, you can have also local conversion that depends on your local system. So that is possible now. It's not that easy to use, but that's mainly the fault of the complexity of time zones in the world. And for those who want to know that, yes, if there's an update in the time zone database, you can even, well, usually it comes with your operating system updates. So anyway, your system reboots. But even in a running program, we have support that you can reread your local operating system specific information about the currently supported time zones and their offsets, etc., and can, while the program is running, do some things. That especially applies to mobile phones, where mobile phones might run while time zones change. Okay. So finally, we have different clock support now. And we have a couple of clocks. So you have just seen system clock now, which we had the system clock since C++11. We now specify that system clocks epoch 0 point is UTC, so it's bound to UTC if you print it out. And but we have other times like the official UTC clock, that's here, UTC clock. So what is the difference between a system clock and a UTC clock when the system clock is bound to UTC? And we also have GPS clock and TIE clock. TIE stands for the International Atomic Organization, so atomic time. So, and to understand that, let's look at the output of this program, and you will see the different abilities of these clocks. And as you can also see, you can convert by a clock cast, one clock to the other. So here you see the system clock. And the real difference they have is they deal differently with leap seconds. So this is a system clock. The system clock does not know leap seconds. So what happens, I just have a loop here over the end of 2016. So just 1 second before the beginning of the 1st of January 2017, we iterate over that. So if you print out this with your system clock, you see that something strange happens because that was the last time we had a leap second in our world. And you see here that we have here the last second of the last hour in 2016. But here we have the leap second, and you get a very strange value for 1 second, with it, which is the closest value we can have to the next second. So we have 23 hours, 59 minutes, 59 seconds, and 999 milliseconds, for example. And it depends on your granularity, what is used there. So for this time, this is just the time we have. And then here we have New Year, 1st of January. A UTC clock is a clock that deals with leap seconds. So this clock, you see, has a 61st second in the last minute. So here we have here the second 60, and count that up. And also the other two clocks have this, but they handle it differently. They just say there are no leap seconds. If there's a leap seconds, we go to the next hour. And that means with each and every leap second, your clock is off by 1 second. You can see that the GPS clock, by definition, for example, was before this leap second 16 seconds ahead, and now it's 17 seconds ahead, and now it's 18 seconds ahead. So that's GPS, and TIE has only a different offset, but the same issue. They have an offset of 37 seconds currently. So because they have different epochs where they were in sync with the official time. So that is done. But the interesting thing of this example is that this is supported by this library, and you can deal with the time data that comes from a GPS system, from a TAI system, but you can also deal with leap seconds if you like, and you can convert these different time seconds to one to each other. That's it. That have been my favorite examples so far. I hope it was fun and you learned a few things. I have here just the last slide, and let me say something. As you know, I currently write on a C++20 book, C++20, the complete guide is not complete yet. There's so much to write. It only has 270 pages, but it's available since this week, since Monday of this week. And for a reduced price, You get all updates for free. So if you're interested, you can read it and you can give me feedback, which the future versions of this draft book will benefit from. Just by preparing this talk, by the way, I learned a few things, and I have to update the content. Yeah, so I think half of the content is there, but key things like the things I just described are all mentioned. A few things you didn't hear about, like modules and coroutines, for example, but that's also the fault that they both are only partially supported in the standard now, or we have to find out things, how things work in practice over the next years, and we'll update and publish things in C++23. That's it. I like C++20. As usual, there are flaws. You have to keep care, but a lot of things are getting better. If you have a question right now, we have 1 minute left. So if you have one, feel free to ask. Otherwise, we can go in the chat or in the, oh, there are many questions in the Q&A, and the Q&A is where? Many questions in the Q&A. That's probably in Discord. Let's see, let's track all discussion.
No. It's at the bottom of your Zoom controls. So if you go to your Zoom, sorry, if you go from the top, you should see the controls drop down as Q&A. If you move your cursor on the top.
So there are a lot of. I don't see a lot of.
You should. There should be a Q&A.
You mean the Zoom chat?
Yeah. So you could go back to Zoom, and then if you hover the top of the screen.
Oh, now I see there's a Q&A. Oh, yes. I see. Oh, thanks. So let's see. Core guidelines explains that we should avoid concept that only asks for features. Instead, a concept should express semantics. Well, first of all, there was something I showed you. No, that's too fine-grained. Don't just ask for a specific method. That's right. I'm not sure whether this goes so far that we only care about semantic features. I would guess we have the same thing as we have for functions. So what is a good function? Is it short or is it long? And if you have many short functions, is it worse or better? I would say here, let's find it out. But we agree that it's not the goal to have a huge amount of concepts. So yeah, instead of concepts, you could also use just Boolean expressions to put constraints, but constraints can't be defined as type constraints, so in front of an auto parameter, when not using a concept. So we are getting an interesting discussion here, and we will find out. So why should one prefer STD ranges for each instead of range for? As you like. We don't have parallel execution for ranges now. So a parallel execution might be an argument then to switch to the range-based algorithms instead of the range-based for loop. And everything else is something that some people like to see. The range-based for loop, sometimes they like to have the algorithm. Yeah. So again, I think this is a matter of taste. Ranges have unfortunate compile time. Is it worth this in comparison to the classic algorithms? I want to measure that. And please give the compilers a little bit time to check this out, how expensive it is. All my answers are, let's find out the right way to use it. Okay. about the chord class, you define the operator, output operator in terms of format. You did not make the class directly usable in format. Loic, thanks for this request. Yes, you can extend the format types, the format mechanism for your own types, which you can do, which is a little bit more work. I just wanted to show you the low-level API. If it's worth it, yes, you might extend the format mechanism so that others can just use your core type and just one parameter as a whole with curly braces, but you would definitely need more code for that. Please also know you can improve some things. So for example, with format, we create a string which allocates memory, and then we write it out to the standard output by using something like std format to n, for example, or format 2. You can directly write to an output stream buffer and make this cheaper, or to pre-allocated memory. Okay, yeah, what happens if -1 is not in the input range? Yeah, I think this is undefined behavior. Don't do that. Okay, so to make your algorithm a bit more smarter, then you have to, you have to do something different. That's it. Okay, thank you very much. I'm a little bit available in the Discord. No, not in Discord, or maybe in the, how is it called? I forget all these names. Gather Town. So thank you very much, and have fun with C++20. Give me feedback if you learned something that's worth to be documented for others. Thank you. Goodbye.